reactants in the products kind of like link the ones that look the most similar. So which one looks the most like H3PO4? H2PO4. So do you see that those look the most similar? So if those are the pairs, then what happened to H3PO4? It lost hydrogen, right? So it lost a hydrogen ion. That makes it a acid. And then that means that H2PO4 minus is the conjugate base. So remember that when you find the pair, the one that loses the hydrogen ions, that is the acid, then that makes its pair the conjugate base. So just remember the conjugate base would then gain a hydrogen in the reverse reaction. So that's why it acts as a base. The conjugates are always on the product side. Acid or base is always described on the reactant side. So then looking at the other one, do you see that H2O and H3O plus, those are sort of the other pairs. Can you see that H2O gains the hydrogen ion to become H3O plus? So that means that H2O is the base. So if it gains the hydrogen, it's the base. If it loses the hydrogen, it's the acid. And then on the opposite side, on the product side, that means that now H3O plus is going to act as the conjugate acid in the reverse reaction. So I just put CONJ for conjugate, just sort of an abbreviation. Okay, next one. So what is the pair to CO3 2 minus? So you see the HCO3 minus is like the most similar looking molecule. So then you just ask yourself, well, what happens? It does what? Gains that hydrogen, and so that makes it a, so it gains the hydrogen, so it's a base. And that means now that HCO3 minus is the conjugate acid. So now in this one, looking at water, and its common pair. So the water loses a hydrogen, so it goes from H2O to just OH. So it's one hydrogen down, loses a hydrogen ion. That means now it is the acid. And that means this is the conjugate base. So notice in that, you can't ever say what water is going to be. Water sometimes can act as an acid. Water can sometimes act as a base. It really just depends on if it is the one that accepts the proton or loses the proton. So last one. So H3PO4, its common pair is, finding H2PO4. And so you would say that it's an acid because it loses a hydrogen ion. So it is the acid. That makes H2PO4 the conjugate base. And then when looking at NH3 goes to NH4 plus, most similar pairs, they look alike. So then you just ask yourself, what happened? NH3, gains the hydrogen, and that makes it a base. And that makes NH4 plus the conjugate acid. Okay? So they're really just make sure that you go back and practice it a couple of times, kind of maybe write yourself sort of a simple description on how do you recognize the acid, how do you recognize the base, and then also remember that in an equilibrium reaction, the conjugate acid always converts into the acid converts into the conjugate base. The base converts into the conjugate acid in these types of reactions. So now I had one question down at the bottom where I left some space. So in this bottom reaction, H3O-PO4, this one, what would happen if this reaction's at equilibrium, but I add NH4 plus? That would upset the equilibrium. Which way would the reaction shift? Away. So would it go to the left or the right? Just going to go to the left. So the reaction would shift to the left. Do you see that NH4 plus is on the product side? So if I add product, the reaction would shift away from whatever I added, which would cause it to shift in the reverse or shift to the left. Either way you can think about it, the reaction would shift towards the reactant side, making more reactant to be able to reestablish that balance or equilibrium. So remember, anytime you add to a system at equilibrium, the reaction will always shift away from whatever you add. Doesn't matter if I add product or reactant, just remember if you add, it shifts away. You just have to figure out what it is that you're adding, if it's a reactant or product. That way you can figure out the direction that it goes. Now, if I remove anything, the reaction always shifts which way? Toward whatever I removed. So if I remove H3PO4, you have to find H3PO4, whether it's a reactant or a product. And remember, that means the reaction is going to shift towards whatever I removed. So which way would the reaction shift? To the left or right? To the left. Right, so see the H3PO4 is on the reactant side? So that would cause the reaction to shift to the left to try and replace whatever is removed. Okay, so those are sort of the ones that we were doing and working on last time. We finished up when we were talking about the fact that water forms ions, but at a very, very, very small amount. And so they came up and said, okay, well, if water forms ions, it actually forms acid and base ions that are equal. So the hydrogen ions, the hydroxide ions are exactly the same with water. So anything that has more hydrogen ions will be an acid. Anything that has more hydroxide ions will be a base. And so this is sort of just looking at this variation. It's kind of looking at the relative amount of acid or base that's present in a solution. So they said, well, if water has 1 × 10⁻⁷ molar concentration of hydrogen ions, then as the concentration of hydrogen ions increases, the exponent would decrease and the acid concentration would go up. As the hydrogen ion concentration decreases, less, as you have less and less and less, then your exponents would get larger and larger and larger. And so the base numbers represent very low levels of hydrogen ion, because that's kind of the red or pink little scale. So pH is really measuring that H3O plus or hydrogen ion concentration. So bases have very little, which means that they're like 0.00000000001, lots of zeros. So they have a really large negative exponent value. So instead of using these exponents and talking about it as a concentration, pH takes the exponent and really converts it to a whole number. So that's where this pH scale of 0 to 14 came about. So the way that you define pH is by taking what is known as the log. So log really is taking and putting a whole number value to an exponent. That's really what log represents. Anything that has a pH below 7 is going to be an acid. So anything like 6.999 or lower is acidic, and it can go all the way down to 0. Anything that's above 7, so 7.001 and above, all the way to 14, is considered a base. And if it's exactly 7.00, then that's the neutral. So that's where a hydrogen ion and hydroxide ions are exactly the same. So you can kind of see this, how this fits into some general things that you come in contact with. I think it's easier to kind of think about acids and bases relative to stuff that you have been exposed to. So look at here, right at the neutral, there's pure water. So this is like distilled water. Tap water may not necessarily be exactly a pH of 7, but distilled water, like what we use in lab, is pure water. There's nothing else in it. So that has exactly equal hydrogen and hydroxide ions. And so that is our pure neutral. So as we begin to go up, everything that's above 7, they have in that kind of bluish scale, they call it basic. Anything that's above 7, all the way up to about 10. So in this range, these are things that do have hydroxide ions. They are bases, but they don't have a lot of them. So they're close to neutral. they're a little bit basic. They call these mild bases. Most mild bases, they're not very corrosive because they don't make a lot of hydroxide ions. So they're called a mild base, or they're described as being mildly basic. And just think that means that there's less OH. There's less ions to react. So here you can see like blood, the ocean, right? So egg whites, okra would all fit into this category. Those are really the only foods I can think of that are in the base level because they're kind of slimy, kind of slippery. Then going up further, baking soda. You brush your teeth with baking soda. It's kind of a good scrubber, but not bad to come in contact with. Even soap. So remember, you tested your soap that we made in lab and you found it was really basic. Well, if you let your soap sit for a month or two, it would be more in that 9 to 10 range. So not very reactive. That's why I told you if you took your soap home, don't use it yet. It's got to sit. It's got to finish reacting so that it's not so basic. Okay. But anything that's above ammonia, oven cleaner, Drano would fall into this. So Drano dissolves grease and hair that's in a clog in the pipe to break that clog up. Most people, I don't know, how many of you have ever seen oven cleaner? Like some of it, this is an aging thing because some of you are like, what do you mean oven cleaner? You just hit self-clean and walk away, right? So most people have an oven where they just have the self-cleaning, and all it does is it heats the oven up super hot and it actually burns all of the organic molecules, and all that's left is the ash in the bottom, which is primarily salt. So all the sugars, all the starches, all the proteins, those things all burn off because of the high temperature. But when I was a kid, before we had a self-cleaning oven, we used to use this stuff called Easy Off oven cleaner, where you would like heat the oven up, you would like spray this stuff in, hold your breath while you were spraying it, because look at the pH of it, okay? The pH is 13. When you go to clean it, same thing. You'd like hold your breath, wipe out as much as you could, and then like get away from it because it would like almost take your breath away. Has anybody ever used that cleaner called White Lightning? That's another one. That's a really strong base. People like spray it on their like showers and stuff to try and kill mold and get rid of stuff. It's a little strong. So like you get a really good whiff of that. It's pretty overwhelming. But all of these that are in this range, these are very strongly basic. Strongly basic, high pH going from 10, 11, 12, 13, 14. These are all things you try to limit your exposure to because lots of hydroxide means it's very corrosive. So a long-term exposure to these can cause chemical burns. So they would call these strongly basic. And just remember that means lots of OH. Lots of hydroxide ions, very corrosive. We can go down the scale as well, and it's really the same. Just below 7, really going all the way down to about a pH of 3 to 4. These, saliva, milk, rainwater, these are things that you don't try to protect yourself from. Even urine, coffee, tomato, beer, soda, a lot of the foods that you eat, those are all going to be in this range or neutral, most commonly. These they called mild acids, or they say that they're mildly acidic because they don't make a lot of hydrogen ions. So remember, those are the reactive ions. So not as bad if you come in contact with it, cause less issues in terms of irritation to the skin or tissues. But once you go below 3, 2, 1, and even 0, as you get lower into this range, stomach acid is down around a pH of 1. It's a little more acidic than lemon juice. And so you try to limit your exposure to these because these are very strongly acidic, which means that they make lots of hydrogen ions. So you can kind of think of things of 0 to 3, strong acids, 10 to 14, strong bases. But everything that's closer into that 7 range, they tend to be mildly acidic or basic, depending on which side of 7 they are in. So now looking at these, let's do some calculating. So this is really the only math on this test, okay? If you haven't grabbed a calculator, there's calculators that are in the box, so you may want to go ahead and grab one. The big thing is making sure that you practice this a couple of times and you write down the steps to be able to complete these. If we run out of calculators, I have a few more up front. Okay, if you need there's two down here, Abby, if you want to grab those two. Okay, so in calculating pH, it is really taking the log of the concentration of the hydrogen ions that are present in a solution. And so, for example, in this one, it says, okay, so you have a 0.050 molar hydrochloric acid solution. So you know this HCl is one of those ones I told you was a strong acid. So HCl, H2SO4, and HNO3. So sulfuric, hydrochloric, and nitric acid are really the ones, if you see this, then you know that when I put this in water, HCl 100% forms hydrogen ions. So the concentration of the acid is the concentration of the hydrogen ions. So all I have to do is take the log value for this. Now, if you have a old calculator, the old calculators, like what I mean by my calculators, my calculator, you actually can't put it in according to the way it's written. You always have to put in the concentration first. So in an old calculator, you will have to put 0.050. That is the concentration. Then you hit log. So same thing, you hit the log button, and then you hit that little plus. Do you see the plus minus sign in the old calculator? It's down by the equal sign. I always call it the plus minus button, because all it does is change the sign. I always think of it as plus slash minus, but on the button on your calculator looks kind of like that. If you have a graphing calculator, put it in the way it's written. Okay, so a graphing calculator, you just put minus, then you hit log, and then you put in the concentration. So it's really straightforward. They don't have to have the value first like an old calculator does. So a new calculator, you just put the plus minus button, and then the log button, and then 0.050 and equals. You just put it in straight in. Okay, so when you do this, did everybody get 1.3? I got 1.301029996. Anybody not get that? I just want to make sure that you know how. This one's pretty straightforward because the concentration has no exponents in it, but this is sort of the way that you're going to solve this every time. So the reason they give that answer of 1.3 is because 0.050, two significant figures, so that's why they rounded it to 1.3. So you still do use significant figures. It is a multiplication, so you're going to make sure that you always round your answer to the number of significant figures in the concentration. If you're going the other direction, so say that I have a pH equal to 6.28, and I want to know what is the hydrogen ion concentration. I want to know what is the acid concentration. You might see it written as what is the H3O plus concentration, or it might ask what is the H plus concentration. All of those are exactly the same. So the concentration of the acid, the H3O plus concentration, or the H plus concentration, all saying exactly the same. Just three different ways of writing the exact same question. When you do this, you're really doing like the reverse steps. So if you have a graphing calculator, so the newer calculators, you will put in the second button, log, and then you'll get the parentheses, and you have to put in the negative value of the pH. So you have to put a plus minus and the pH, and then equals. If you have the old calculator, you have to put the number in first. So you put in the pH, then hit the plus minus button. So first put in the pH, then do this, and then hit the second button and the log. Okay, so in this, I've got an old calculator, so I'm going to put in 6.28. Then I hit that plus minus, so it's a negative 6.28. And then I hit second and log. And I got 0.000000525. Anybody not get that? How many zeros? 6. 1, 2, 3, 4, 5. 5, 2, 5. And that's molar. Concentration is always in molar with this. Okay? Now, if you have an old calculator and you're like, or if you have a graphing calculator, you might see this in exponents now. So here's how to change from normal to exponents to scientific notation. So if you hit second in the number 5, that will put your answer in scientific notation. So if you have an old calculator, second in the number 5, and you should get 5.248074602, and then a negative 7. Okay, so it would say, if I had the graph, if I had it in scientific notation, 248074602, and then times 10 to the minus 7. So you might see this on your calculator. Same thing. One is just written out in long form. The other one is written in scientific notation. So put yourself a note if you're using one of my calculators. Second and number 5 puts you in scientific notation. Second and number 4 changes you back to regular. I'm not sure if you have a graphing calculator, if yours probably shows up with the.
Put the 6.28 as the pH, right?
Yep.
Okay, so I put that in, and I got the bottom number, the 5.2.
Right, they're the same number.
So, okay.
Those are the same number. One is just written in expanded form. The other one is written as scientific notation. So notice that 5.248, they round it to 0.000000525. Okay, and in fact, that one's okay because it's 6.28, 3 significant figures. So I could just use that top number. If I was going to use the bottom number, I would round that to 5.25 times 10 to the minus 7th, because 3 significant figures is what I would end up keeping. Remember, with exponents, you just round that front part. Don't leave off the exponent number. You need that times 10 to the minus 7 part, because that's telling you where the decimal place is. Well, in either one, like, so if you took this one, you would put 5.25 times 10 to the minus 7 molar. That would be your answer. You would round that. Do you see that those two numbers are exactly the same? One is in scientific notation, the other one is not.
But I just wondered if you preferred one or the other.
It doesn't matter to me, okay? You could do either, like, because I can see that those two numbers are the exact same number, just one's in with scientific notation, the other one is not. Okay, so let's practice a couple of those just to make sure you can put them in. So here's the first one. So what is the pH of a 2.65 times 10 to the minus 5th molar HCl solution? So this one, you've got this exponent. So you've got to make sure you know how to put the exponent in to be able to solve this. So you kind of got like a dual thing. So here, remember that EE button. So I showed you that when we did like molecules, when we were doing Avogadro's number. So that button, Andrew, you might want to grab a calculator if you don't have one. So that EE button really comes into play because remember, that's going to do that times 10 to the whatever. So in this one, if you have an old calculator, you've got to put in the concentration. So how are you going to put this in for your concentration? Okay, so you put 2.65, then what? Then EE, and then what? A -5. Okay, so if you have an old calculator, put that in. If you have a graphing calculator, you probably know how to put your exponents in anyways, so you just do them straightforward. If you have a graphing calculator, put your plus minus sign, log, and then the concentration. If you have the old calculator, then make sure that you first put in 2.65, EE minus 5, then hit log, and then the plus minus symbol. So 2.65 EE, log. No matter which way you did it, Did everybody get this? That's a 5. Anybody not get this number? 4.5767544126. Hand raised if you didn't get it. I want to make sure that you're putting it in right. That's the big thing. It's like putting in the exponents is a challenge, but then making sure you do it in the right order. What's this? Yeah, that's your plus minus. Your plus minus button, no matter what, is almost always down next to your equal sign.
So we put,
So yours, so you could use the EE if you want, but you will put minus and then log. And then you've got to put that in. So 2.65 and then see. Nope, go back, delete that one. Yeah, so then you go, so to get this, you can go second EE, and then you put minus 5 equals. See the EE, you can use it, you've got it on yours, so if you find it, I think it's really easy because you don't have to put parentheses around stuff. If you put the EE in there in your number, it automatically puts the brackets around it. Did you get it? Okay, try the next one. If you got that one okay, try the other one because this one's like the reverse. What's that? For you, it's just the minus in parentheses. And then log. And now put that negative 5. Yes. So write it down. Don't use like your minus sign instead of the plus minus. Like that was the problem she was having, trying to put in that exponent. Make sure you use a little plus minus sign, not a negative. Okay, so in this one, old calculator, you got to put in 1.68 first, make it negative, then hit second log. 1.68, make it negative, second log, because that's the inverse log. If you have a graphing calculator, you do it straight. You hit second log, then the negative, then whatever the pH value is. I got 2.089296131 times 10 to the minus 2 molar. Anybody not get that? Okay, I just want to make sure that you get that you're able to do the calculation for that. Did you understand the steps? Maybe write it out underneath here, whichever one that you're actually using. So if I had to, I've got to round this with this answer. So what would this answer end up being? 2.09 times 10 to the minus 2. Now, if you're in English, like regular expanded, then this would actually be 0.0209. Do you see that those are exactly the same? Okay. Do you see both? Either one of those numbers would be perfectly fine. And again, if you have the old calculator, if you hit second flow, it'll actually put it to the bottom number, the expanded. And if you hit second psi, it'll put it in scientific notation on the old calculators. If you have a graphing calculator, I can try to help you figure out how to do it, but I don't know, like, just off the top of my head. Most of the time I'm like, I don't know. Okay, so just know those are the two. These are exactly the same. That's a decimal place. So this and this, those are exactly the same. So we'll do one more, okay? So here's another one. So what is the pH of a sample of sodium hydroxide with a hydrogen ion concentration of 1.45 times 10 to the minus 12? And then what is the hydrogen ion concentration of a substance with a pH of 8.35? So not only do I want you to answer those, but also identify, are these samples strong acid, strongly acidic, weakly acidic, or mildly acidic? Are they strongly basic, mildly basic, or are they neutral, right? Because based on our little pH scale that we kind of looked at, you should be able to identify, based on pH, where it falls on that scale. So give you a couple minutes to answer that. So Vaughn, you probably want to grab a calculator to make sure that you can put these in. Kristen's here. Jay. So on yours, you hit second log of negative 8.35. And don't hit the negative button. Make sure you hit the plus, that little plus minus button. Yeah? That work? Okay. Okay, so in this one, putting this number in, things that I got. So I got, one of the things that I got was 11.838632. And then I had somebody in class last night was like, but I got 1.1. Did anybody get that? Did anybody see the like a 1.1? What they didn't notice is I saw someone got 1.183863 times 10 to the first. So if you were in scientific notation, it might have changed it to this, especially if you got the old calculator. Do you see those are the same? Times 10 to the first means the decimal place has just been moved over 1. Those are the same numbers.
Is the H2O plus, is that the concentration?
Yes.
Okay.
Yep, so in this, so that's the, remember the concentration of a strong acid or base, you just put that directly in as the acid concentration. Okay? So what would I have to round this to? 11.8. Okay, 11.8, because do you see that my concentration 1.45, 3 significant figures. You don't count any of the exponents, you just count the number in front. 3 significant figures in my concentration, 3 significant figures in my pH. To get this? Okay, so what kind of calculator do you have? Old school? Okay, so for the old one, you have to put 1.45 EE minus 12.
That's where I was wrong. That's why I didn't get it right.
Right? That's why I want to practice, because I want you to make sure that like putting these exponents in that you're like, oh yeah, don't forget the EE. Okay? Now hit log and then make it negative. Good? Yes? Okay, so when you put in, so this is kind of like twofold. One is remind yourself how to put exponents into the calculator that you're using. Okay, you've got to be able to put the exponents in, and if you have a graphing calculator, you just put the formula in exactly as it is. The plus minus button, log, and the concentration. If you're using an old calculator, you got to put the concentration first in. Make sure you use the EE to do that, and then go from there and put in the log, then make it negative. It's kind of like you work backwards. All right, so bottom one. So 8.35. Oh, so next question, 11.8. What would you call that? Strong acid, strong base, mild acid, mild base, or neutral? Strong base. Good. This is a strong base. Based on that pH scale, anything really above 10 is considered a strong base. So now this one, hydrogen ion concentration of a substance with a pH of 8.35. So if it has a pH of 8.35, what is it? Yeah, and I would really, I need to change the wording because I always think of weak electrolytes. It doesn't mean it's necessarily a weak electrolyte, it just means it's really dilute. It doesn't have a lot, so it's really more mildly basic. Right, so this would be a mild base or mildly basic because it's above 7, but it's below 10. So anywhere in that above 7, below 10 range is more of a mild base like ocean water, like your blood, okay? All right, but we want to calculate this. So to find the hydrogen ion concentration, it's the second log of the negative pH. So if you have the old calculator, put the pH 8.35, hit the plus minus button, then do second log. If you have a new calculator, graphing calculators, you just hit second log and then put a negative plus minus, not negative, the plus minus button, and then put in the pH and equals, and it should be fine, okay? So I have to go 8.35, make it negative, and then second and log. And if you're in this one, looking at in just expanded, 1, 2, 3, 4, 5, 6, 7, 8. I got 1, 2, 3, 4, 5, 6, 7, 8, 4. Did anybody get that? Okay. How many significant figures do I need though? 3. So do you see that leaving it in expanded form on the old calculator, it doesn't give me 3 significant figures. I've got to go to scientific notation. So to go to scientific notation, you're going to hit, and this is only the old school calculators, you hit the second button and the number 5. And now you should see 4.466835922 times 10 to the minus 5th. No, 9th, sorry. My eyes. Anybody not get that? Okay, so on yours, you hit second log negative 8.35 and equals. Not the plus minus button. Do you know what which one that one is? That's like, if you put the minus button in, it's gonna go to syntax error. It goes and gives you all kinds of crazy. So you're going to hit, to do this one, you go second log negative, this negative, and the number is 8.35. Okay? Okay, so write the steps down so that you have, make sure you write the steps down so that you know which way to follow it, because that'll be something that you probably want to put on a note card. If you're like, I'm gonna get them mixed up, just write like which buttons, like this button, then this button, then this button, then this button. Just write those ones out so that you make sure that you don't end up missing it when you don't need to. Okay? So everybody got this. So now final answer would be what? Yes, 4.47. 4.47 times 10 to the minus ninth, that's molar. Make sure that you don't round. Don't leave off the exponents. You have to keep those. But remember, the numbers out front are the ones that are, you take the significant figures into account. Okay, so there's one more. I'm not going to do this one. There's 3 right here. I want you to practice these. Try and do it like today or tomorrow, if at all possible, because if you can practice them, making sure that you know how to put them in, then that's going to be beneficial. We'll do those ones next time just to make sure that everybody's kind of up to speed. But just writing those steps out on what you need to do in order to be able to solve. These are really the only 2 ways you got to go. You got to go from concentration to pH or pH to concentration. So it's really just one or the other. There's no other sort of strange ways of trying to solve for them. Okay? All right, so this leads us to the last topic in this chapter. So the last topic in this chapter is one that you may come in contact with if you're dealing with somebody that is severely ill. Any living thing, could be an animal as well. If their fluid and electrolytes get out of balance, another common one that gets out of balance is their blood pH. So normal blood pH is from 7.35 to 7.45. So when you think of that pH scale as 0 to 14, that's pretty narrow. That's within 1/10 of a pH point out of a 0 to 14 scale. When it goes too high, they call that alkalosis. So alkalosis is if your blood pH goes above 7.45. What begins to happen if there's too much base in the blood, that hyperstimulates the nervous system. So what your nervous system starts doing is kind of going haywire. Common symptoms that you start to see in a patient that's having their pH going above 7.45 is that they begin to get kind of like nervous, anxious. They may actually be trembling. They may seem disoriented because the nervous system is having a hard time processing things normally. This can actually lead to convulsions if the pH is not remedied and continues to climb. Worst case scenario, this can actually cause heart arrhythmias. An arrhythmia is what? What's a heart arrhythmia? Skips a beat, or you could really just think it causes an irregular heartbeat. So instead of the normal beat pattern, you start to see it starts to get kind of erratic, so you don't have like the normal parts. And if that continues, that can actually lead to cardiac arrest. So your heart can begin to fibrillate or beat without any control. So extreme alkalosis can cause death. Opposite side of the coin, if pH goes below 7.35, there's too much acid in the blood. This is actually much more of a common occurrence. Hopefully nobody ever has to deal with anything like this, but of the two, acidosis is much more common. So as the pH begins to drop, while alkalosis stimulates the nervous system, acidosis actually shuts the nervous system down. So the nervous system stops responding. So this patient may seem very tired. They may seem very confused again. Both cases can cause confusion because the nervous system's not working the way that it needs to be able to process information. They may sometimes seem drunk, okay? They're drunk, then they're sort of more slurry, and it's all because they're more delayed in nervous system processing. As acidosis progresses, as it gets worse, they can actually lose consciousness. So you find somebody, so then oftentimes they think like somebody that has this acidosis that's found, they're like, oh, they must have drug overdose, they must be drunk, like something happened like that. It may actually be because of the acidosis that they're actually unconscious. Worst case scenario, untreated acidosis will suppress the nervous system to the point that you stop breathing. And if you stop breathing, you're not going to survive for very long. So in extreme cases, changes in your pH can cause death. So I will tell you, like, this is acidosis. This is much more common of an issue that they have to deal with. But 99.9% of people never experience this. Okay? So the odds are out of 100 people, maybe one. 1,000 people, maybe a few. Okay? So it's not very common because there are things that you can do to help to counter this. So buffers are the number one way that you actually maintain this balance. And it's one of the reasons we talked about acids and bases and conjugate acids and bases, because a buffer is present in all of your body fluids, and buffers are made of a weak acid and its conjugate base, or a weak base and its conjugate acid. So you know, if you have an acid and somebody and there's base added, what do? Acid and a base do what? What's that called? If you add an acid and a base, they neutralize each other, right? So acid and a base make salt and water. So in your fluids, you have a weak acid, and that can react with any added base. You have a conjugate acid or conjugate base, and that can react with any added acid. So you really have like an acid and a base pair sitting in your blood, sitting in your cells, sitting in even your saliva. And so any added acid or base gets neutralized. So it helps to maintain this balance by holding this pair. This is why any kind of added acid or base gets neutralized quickly and doesn't affect your pH. And that's why 99.9% of people never have an issue. Buffers are like instant. They're sitting right there. So if there's acid that comes in, like think about digestion. So you eat a bunch of tomato sauce, that's really acidic. That means there's going to be more acid than normal absorbed in digestion. Buffers can balance that out. So the buffer then balances it and keeps your blood pH between 7.35 to 7.45. It has to be a pretty extreme change in order for a buffer to not be able to handle it. So something that can happen is what they call one of the imbalances that causes acidosis. They call it respiratory acidosis. So acidosis means there's too much what? Too much acid. So acidosis means too much acid in the fluid. In this case, we're going to talk about the blood. They call it respiratory acidosis because there's some kind of issue with your respiratory system. So this is an acidosis that's caused by a lung problem, caused by a respiratory problem. So here's some examples of that, okay? If somebody doesn't breathe enough, like you think, like, why wouldn't they breathe enough? Okay, so alcohol intoxication. Alcohol actually suppresses your nervous system and it can slow your heart rate, it can slow your respiratory rate. So if you're not breathing enough, then that means that not breathing enough, that means carbon dioxide begins to build in the blood. When carbon dioxide builds in the blood, this is an equilibrium reaction, right? So if I add carbon dioxide, which way is my reaction going to shift? It's going to shift away from what I've added. So that causes the reaction to shift, and that creates more acid. So under normal circumstances, your buffers balance it. The acid gets neutralized, it's not a problem. But what if you just keep adding acid, adding acid, adding acid, adding acid? You only have but so much conjugate base. So if you overwhelm the buffer, now your blood pH can begin to drop. So this is a problem in, like, when you've heard about people that have died from alcohol intoxication, this is typically what happened. They stopped breathing, they didn't have any kind of medical intervention, the acid levels built up in the blood so much that it actually impaired respiratory function, and then they died. Other causes, though, most of the time, these are because of lung damage. So there is a condition called COPD. Does anybody know what that stands for? Chronic. Obstructive pulmonary disease. Good. So this, chronic means what? What does chronic mean? Long term. Chronic means long term. Acute means it just suddenly happened, right? But chronic means long term. So COPD does not develop overnight. COPD is something that develops over years, sometimes even decades, before you really start to have respiratory impairment. Typically, people that develop COPD, they have had respiratory infections more than twice a year. They've had pneumonia, they've had bronchitis, they may be an asthmatic. All of these, though, end up causing scar tissue in the lungs. So scar tissue means that you don't diffuse oxygen and carbon dioxide as well. So patients that are asthmatic, they can also develop respiratory acidosis, because what happens with an asthmatic? If you're having an asthma attack, what happens to your airways? They close down. So think of, like, the tubes going into your lungs are this big. So for an asthmatic, the tube gets really small. So can you imagine the amount of air that moves through that tube that's supposed to be this big, and now it's like 25% the size? So if you've ever been or seen or had an asthma attack, this sensation of where they're like trying so hard to pull air in, but they can't because the tubes have gotten too narrow. So that means if the air doesn't get all the way to the air sacs in the lungs, you don't get good diffusion. Carbon dioxide begins to build up. They can end up having respiratory acidosis. The last one, so COVID had a huge range of ways that you actually see it. I don't know that we'll get to talk about it in chapter 11, but it's really kind of interesting. But I've known people that had COVID that had like a runny nose. I've known people that had COVID that had flu-like symptoms. They ran fevers. They felt like they had the body aches, massive headaches, lasted an entire week, like felt horrible, but no respiratory symptoms at all. Didn't have a cough. One of them said that their throat kind of hurt a little. So it's just really odd. But then I've known people that had COVID that got like severe pneumonia, respiratory, had to have a nebulizer, had to be in the hospital, ended up on a ventilator, like all of that. So depending on how that virus actually settled in your body, whether it just caused more diffuse kind of flu-like symptoms, or if it really attacked your respiratory system. I know somebody that ended up having to have open heart surgery because of COVID, because of damage to vessels in the heart, like this whole big range. It's really kind of an interesting one because of it doesn't just do one thing. Like chickenpox just makes you break out, right? But COVID's kind of got like all of these different potential symptoms that you may see. And so some of them, though, the ones that had the respiratory system really attacked, ended up with a lot of scar tissue, a lot in that. So basically it's like they now have COPD, and that happened purely because of COVID. They describe when they look at x-rays of their lungs, it looks like shattered glass. So that looks just kind of like cracking all inside of the lungs. That's all scar tissue. So unfortunately, some of them now are like on lung transplant lists, trying to actually get a new set of lungs because their lungs are barely functional. So those are all possible things, but anything that either affects the ability of air to get into the lungs or damages the ability of oxygen and carbon dioxide to diffuse can cause respiratory acidosis. So if you have a patient that comes in and their blood pH is below 7.35, some of these patients can have blood pHs in the 6s. Not just like 7.30, but like even down into like 6.8, 6.9. That's really bad. If you see that, that means like your nervous system is like not functioning the way that it needs to, and everything else is going to start shutting down next. So to balance this, here's what they give them. So straight away, they come in, they do a blood gases, they see that their pH is below 7.35, and they're going to give them bicarbonate. Bicarbonate is one of the blood buffer pairs. So here's our balance, right? So it's the exact same reaction. In your blood, you've got this balance. And you have excess acid for this patient because they're not getting rid of carbon dioxide. So what is the bicarb going to do? If I add bicarb, which way will the reaction shift? Shift to the left, right? So it'll shift it back away from what I add. That helps to balance out that excess acid. So it's going to help to remove the excess acid, helps to bring their pH back up into that normal range. Unfortunately, people that have COPD, that's end stage, okay? So just trying to keep their oxygen levels up and their CO2 levels managed is really all that you can do. It's not something that happens overnight. Like I said, a lot of the long-term COVID pulmonary damage, those people really need to have lung transplants. It's to that case. There's really no improving. Once you get scar tissue in lungs, you really can't repair them. That's just loss of diffusion, loss of oxygen and carbon dioxide. So this is one that you will see. The second one that you will see, they didn't make a chart. The second one that you will see is called metabolic acidosis. Metabolic acidosis, the description that I gave you for alcohol intoxication. So metabolic means it's an internal disorder. It's not something wrong with your lungs, which is why they call it metabolic. So you know that it's an internal imbalance. This can be caused by kidney failure. So remember we talked about dialysis, how patients on dialysis, how their salt, their water, their waste all get out of whack. So their waste can be acidic, can be basic, but it most commonly will cause acids to build up in the blood that normally the kidneys would flush out. So the kidneys can't. So that means now this acid begins to build. Kidney failure, liver failure. Your liver is a big filter, and its job is to convert things that are toxic to things that your kidneys can flush. So if the liver's not working, then those toxins aren't going to get detoxified the way that they need to. Poorly managed or untreated diabetes. Because one of the byproducts of diabetes is a lot of fat breakdown, which creates those keto acids. So it can create so much acid in the blood that it can lead to acidosis. So those are really the three big ones. Those are if a patient comes in and their blood pH is low, but their carbon dioxide's normal. They look at both because they want to see if their pH is low and their carbon dioxide's through the roof, then you know it's a respiratory issue. But they come in and their CO2 is normal, but their blood pH is really low, then they automatically start trying to figure out, okay, what organ's not working the way it should. If it's because of kidney failure, then they might need dialysis. If it's because of liver failure, they might use dialysis, but they're also going to use some other things to try and bring that back. That's another bad one. Liver failure is not a way you want to go. But if it's diabetes, what are they going to give them? Insulin, right? So if it's diabetes, they probably have hyperglycemia, so they need to go ahead and get that under control, start giving them insulin to bring their blood sugar back down so that their body stops making so much acid. So the way when they talk about this treatment, so in the treatment, they have to treat the disease because if they don't, it's just going to come right back. They will give them bicarb again, just like with the other, trying to balance out that excess acid, but then they've got to treat whatever that disorder is. These are really the two big ones that you're going to ever see. You'll see patients come in that are in kidney failure, and this could be dogs and cats as well as humans. You'll see patients that come in that may have liver failure, and you can find that their blood pH will be all out of whack. So they need to monitor this, and it's typical why they would do a blood draw and they would run this to see what exactly are the stats, like what are the red blood cells, what are their fluid levels, what is their pH. Check all of those as a way to try to ascertain, is it kidney? Because then they're going to look at like bun levels and urea and nitrogen waste. Or is it something that's liver? Because then they're going to look at ammonia levels. Or is it something that's like, is it alcohol intoxication? So trying to figure out exactly what is it that's going on to try and treat it, because metabolic, it's not going to fix itself. Typically, you've got to try to stop the acidosis, but then you've got to treat the cause that's creating it. Now, alkalosis, I will tell you almost never see it, okay? You may have actually experienced it. If you've ever had a panic attack and you were like breathing super, super fast, this type of sensation, like I always think of the Blair Witch Project. I don't know if you ever saw that movie, but that girl, the snot running down her nose, and she's like breathing like super fast. She's like shaking, okay? That's really a very common, remember I told you that you get trembly, shaky. So those can that can actually lead to respiratory alkalosis because you're breathing way too fast. You feel dizzy. You feel like you're going to pass out kind of thing. So they try to calm you. Sometimes they have you breathe into a paper bag type of thing. But that's like worst case scenario, you pass out. And if you pass out, your brain will like reset your breathing anyways. Just make sure that they're not near something they can fall on. So get them down low or on a couch or something if they're going to pass out. That's pretty much how you fix that. But if metabolic alkalosis, if you've ever had the flu and vomited until you could vomit no more, like if you're just like couldn't stop, when afterwards you're like super shaky, that is because excess vomiting can cause symptoms of metabolic alkalosis. You lose too much stomach acid. Your body's normally used to absorbing a certain amount of acid from the stomach. So if you lose all that acid, it can trigger or cause the blood pH to go up. It's usually temporary, but that kind of sensation, if you've ever had that sensation of being kind of like weak and trembly, that's typically an alkalosis symptom. So you've probably experienced it at some time or the other. And again, with this, just try and stop the vomiting, try and like get fluids back into the person, and those symptoms usually subside. It's really the acidosis characteristics. Those two at the top are really the much more common ones that you see that require medical intervention. Okay, so the last thing. So I said buffers, 99.9% of the time, buffers are the number one way that you manage pH. What buffers do is they neutralize acids and bases that get added to your fluid. And you have enough acid in conjugate base. So acids react with bases that come in. Conjugate base reacts with any acid that comes in. And that helps to maintain this balance. If the buffers are not like kind of covering that and there's too much acid or base, you can actually begin to breathe faster or slower to try and alter the amount of acid in the blood. So carbon dioxide is carried in your blood as carbonic acid. So if you need to get rid of acid, you'll breathe faster. If you want to conserve acid, then you breathe slower. So you may have patients that will have an altered respiratory rate because of too much acid or not enough acid being produced. So I always think of them as being the backup because they don't kick in instantly. It takes a little while, takes a couple of hours before you really start to notice any respiratory changes. But then far and above, the kidneys. And this is why you really need some kidneys, because your kidney's job is to do the fine tuning, right? So the kidney's job is to filter your blood 35 times a day. As long as you have functional kidneys, 35 times a day, any excess acid gets filtered out. Any excess base gets filtered out. So as long as your kidneys are functioning, they help to make sure that your blood pH really stays like right at that 7.4. Keep it right in the middle, not dropping or raising above or below. So I always think of the kidneys as being much more of like this long-term balancer. So buffers, your respiratory rate, and then kidney filtration are really the three ways you balance out the pH and help to keep it constant through your entire lifetime. Okay, so that's finishes pH, and this is really kind of like the health aspect or connection that I wanted to make with pH, along with just measuring pH. So this rolls us into chapter 10. Chapter 10 is all about proteins. So proteins are, look, it didn't go away. Wonderful. So proteins are really the last nutrient molecule that we haven't talked about. We've talked about fats, lipids, oils. We've talked about their functions and where you find them. We've talked about carbohydrates. We talked about the sugars and the starches and their function. So proteins really are your third nutrient type. This doesn't start here. I was looking at this earlier. Going all the way back to the beginning. Yes. So that's at the very beginning here. And this is actually, Mr. Awadala sent me this, and he thought it was hysterical. So I said, well, I'll put it on my PowerPoint to make you happy. And he was like, great. So what do you call an acid with an attitude? It's amino acid. Yes. That sounds very much like him, doesn't it? Okay. So proteins are polymers. Remember, polymers just means it's a chain of many things, right? Lots of little links. The building blocks for proteins are called amino acids. There are 20 different amino acids that are used to build all the proteins that your body uses. Some proteins are small, like insulin. Insulin is like 38 amino acids long. It's a pretty small protein. But then if you remember when we talked about blood, I told you that you have proteins in your blood. One of them is called albumins. Albumins are huge. Okay, albumins are upwards of 400 amino acids. So you can have little proteins or big proteins. There is a list of some of the functions that you've got there. We will talk about like the 8 functions of proteins as kind of the second half. But when you look at an amino acid, all 20 amino acids have one basic structure and then only one part that's different. So in looking at this, do you see on this one up in the upper right corner, all of the purple part, the nitrogen, carbon, carbon, all of the ones that are written in purple, that's the same for all amino acids. All amino acids have this nitrogen connected to a carbon, which is kind of funny because it looks like Nash Community College. On this nitrogen, the nitrogen is typically positively charged. And so if you have a nitrogen, remember that that's either an amine or an amide. Right? Nitrogens as a functional group, remember they're always an amine or an amide. So that is why amino acids got the name amine in them because of that nitrogen. Now, thinking back, carbohydrates don't have nitrogen, okay? Lipids, there might be a few, but not very many. Only like those phospholipids had some nitrogen. Most lipids are nothing but carbon and hydrogen. So this is where your big nitrogen group comes in, where your nitrogen content, remember we said what are the 4 big atoms in the body, 4 major elements? CHM, right? Carbon, hydrogen, oxygen. There's where the nitrogen comes into play. It's the nitrogen in the amino acids is why nitrogen is considered a main element. So amino side, over on this other side, is a carboxylic acid group. It's lost its hydrogen, but it is an acid side. So that's where amino acid comes from. The nitrogen on one side, the acid group on the other side. Those are all exactly the same. This middle carbon, the middle carbon has a hydrogen. So that is present in all 20 amino acids. This basic nitrogen, carbon, carbon group, nitrogen on one side, carbon with 2 oxygens on the other side. The only way that the 20 amino acids differ is by what hangs off right here. So what's attached to that middle carbon makes one amino acid different from another. Sometimes it might just be a hydrogen. Sometimes it might be a CH3 or a methyl group. There's some examples where it's an alcohol group. So that part, they call it the R group. They named it that because R stands for residue. So that's where the R comes from. But that group is the one part that makes one amino acid different from another. Second thing, though, is that center carbon is actually chiral for almost all amino acids. So if you look, do you see that like above is the acid group, to the left is the amino group, to the right is the hydrogen, below is this R? As long as those R's are different, all 4 groups are different. That means we can have a chiral carbon. So it's not as bad as sugars, which have lots of chiral carbons. There's only 1. So that means that all amino acids, they exist as a right or a left-handed form. So remember in nature, most sugars are what? D or L? Got a 50-50 chance, D or L. D. D glucose. Remember like alpha D glucose, beta D glucose. So D, that D glucose is the difference. Well, amino acids in nature are almost always L, which is just kind of odd that they're not the same, but L is the more common form. So what we'll do next time is we're going to talk about like how are these R groups different. You do not have to memorize the structure of any of them or even the names. We're going to talk about like there's really 3 different groups, like the polar groups, the non-polar groups, and the charged groups, because that really affects how these proteins fold into their specific